In this video, I'm going to continue going over solutions to Math 256 Midterm 2 from March 2015. Here I'm going to talk about problems 5 and 6. So in the first part of problem 5, you're asked to write down a formula for g of t in terms of heaviside functions, the u sub c functions. And I've copied over this figure here, and let's write down what that formula would be. So we start off, the function is 0 up until 2, and then from 2 on up until 4, the function is a line with slope 2, and it goes through the point t equal 2, so that means its formula would be t minus 2, but that's only valid from 2 and above, so we multiply it by the heaviside function at 2. Next, what happens, the function is now going to have to change its slope from a positive 1 slope down to, well, you can see that we go over 2 here and we go down 4. So the slope becomes minus 2. So we have to go down by minus 3 to get rid of the first t here, and then to end up with a slope of 3. So we have a function minus 3 t minus 3. Oh, no, not 3, sorry, we're at 4. So this will not modify it immediately at 4, but it'll start to modify it as you go up from 4, and that will only take effect above, at and above t equal 4. So that gives us a function that tilts down here, but that will continue going. Now we have to modify this last piece. Instead of having our function continue off like this, we want to add enough to it so that the function becomes flat, and that would require that we increase it with a slope of 2, and that's starting at 6. So we want to have a u6 of t in there, and that would give us this function here. What we actually want is to move this guy up to there, which means that we have to further add another 2 everywhere for values of t greater than 6. And so this is the formula that we get for g of t using that approach. Another approach is to use u2 of t minus u4 of t, which will be 0 everywhere except between 2 and 4. And in that interval, the formula for the function is exactly t minus 2. And then add to that, in another section from 4 to 6, we have the formula of the line will be exactly minus 2, and then that has a 0 at t minus 5. And so either of these two will give you the correct answer. They just have a slightly different form. And so what are the point values here? You get a point for each of these terms. And some of you may have included these two together, but as long as you have the right function, that's fine. And then in this solution here, similarly, you have to get the interval 2 to 4 and the notation for the heavisides in that interval correct and the function correct, and the same thing here. So in either of these two cases, there's a total of 4 points available for this problem. Now in the next part, part B, so this was part A. So for part B, you were asked to take the transform of f of t equal, this is a totally different function, u2 of t multiplied by t minus 2 minus 2u sub 3 of t times t minus 3 plus u sub 4 of t times t minus 4 plus delta of t minus 3. So as an exercise, it would be good practice to try and sketch what this function looks like, but I'm not going to do that here. I'm just going to write down the transform. F of s will be equal to, well, when I have a shift like this, I get e to the minus 2s and then I multiply by the transform of t, which is 1 over s squared, minus 2 times e to the minus 3s times 1 over s squared plus e to the minus 4s 1 over s squared plus e to the minus 3s with no function multiplying it. So in this example, there was a single point for getting the e structure to all three of these correct, and another point for getting the 1 over s squared for all three of those, and then getting the delta function transform correct. So that's a total of 7 points for problem number 5. For problem number 6, the goal is to set up a function for calculating a Fourier series, and you'd like to make sure that the Fourier series consists of only sine functions, and you want the Fourier series to converge to the function x squared everywhere on the interval 0, 1, including the endpoints. That means that you have to make sure that there are no discontinuities on that interval. And you're asked to sketch your extension, and you also are expected to state the period of the function and the value of L used in the formula for the Fourier series. So the function that we're interested in is the one that looks like this, x squared. So this is y equal x squared from 0 up till 1. And now we want to make sure that we're using sine functions, so we need to generate an odd extension down here before we turn it into a periodic function on the whole real line. So that's the first step. But if we just copy this over, we would have a jump right at 1. Should move this over a bit. So because we would start with the next section down here, we'd have a jump, and we would not get exact convergence there. So instead, what you can do to fix that is, there are a number of ways of doing this, but we can extend it just a little bit beyond 1 in any way we like, as long as it generates a function that's continuous between and including 0 and 1 when we extend it. So now when we do the extension, we'll have a function that looks like this. And so let's say we do that up till 1.2. and down here till minus 1.2. So now you can see that when we calculate the Fourier series, it'll be continuous. The function is continuous everywhere from 0 to 1, including 0 and 1, which means we get exact convergence of the Fourier series. The only problem is that we'll have a jump at 1.2, but we're not interested in the function matching outside of the interval 0 to 1, so that's not a problem. So now to the question of the period. Here we've extended the function out till 1.2, and then we've pasted it over from that interval to the next. Because we had to extend it as an odd function, the function that we're pasting over periodically extends from minus 1.2 to 1.2, so that means that the period is 2.4, and the L value will always be half the period, 1.2. And that is question 5 and question 6.